Okay, we're going to begin the first session in earnest. Our next speaker is Dr. Bert Semtner. He began his ocean modeling at GFDL, and he's a colleague of Warren. When I was a postdoc at NCAR, I would see Bert quite often. But he began his ocean modeling at GFDL with Kurt Bryan and Mike Cox in 1970. He later pursued increased computational speeds and accuracy on emerging vector parallel, massively parallel machines, together with colleagues at NCAR and LANL. In the early 1990s, he conducted global decadal simulations comparable to those only being now done with high-resolution climate studies. Bert has participated in DOE climate modeling, including Warren Washington's PCM runs. Bert continues to participate and sometimes chair review allocation panels for various federal agencies. So, Bert.
Okay, so I actually moved to the Naval Postgraduate School, but I kept in strong contact with Warren and his group. I moved there after 10 years at NCAR, and this is one of the attractions of going to the Naval Postgraduate School is the Big Sur coastline. And this is talk is based on frequent interactions with Warren in a time period at NCAR for 10 years, and as an NCAR affiliate scientist many times over, and as a colleague continuing thereafter, even recently. So this is going to be sort of a history of modeling ocean and climate, ocean and ice in climate, although it could be and climate under Warren's leadership. So the next slide is basically an indication of Warren's approach over the years as I have observed it. He has a clear goal over the years of making progress on the foremost scientific and societal program of modern times, namely the prediction of global climate change. The strategy has been to use the best available coupled models and run them at progressively higher resolution on the fastest available computers in order to better resolve crucial dynamical processes and surface features so as to accelerate model accuracy and scientific discovery. He has been aided by Department of Energy support to migrate models onto increasingly faster computer architectures and to run them on the fastest available DOE and NCAR machines. And members of his NCAR section, get back to the mic. Members of his NCAR group have provided many of the algorithmic speed-ups so that Warren can concentrate on the analysis and simulations and distribution of findings. So I will kind of beat my own horn for a while, blow my own horn for a while, and talk about a few of the algorithmic speed-ups that I was personally responsible for. And this is how I first met Warren. To make an Understeiner sea ice model, which was based upon Arctic ice observations, was simplified by me in such a way that it boiled down to probably 1/50th of the computational cost that the original model did. And Larry Gates at RAND invited me to go work with Warren and Claire Parkinson doing simulations on Arctic and Antarctic grids in order to validate the model geographically, and the formulation has persisted with continuing improvements since then. In fact, the latest model I know that has used this simplification is in 2004. So in addition, another algorithmic speed up, and this is one of two things that is also mentioned in that list that we just heard of highly visible publications. The dynamics of sea ice was originally originally developed by Hibbeler with a method that was hard to simplify, and it was only made effectively faster by Hunke and Dufowitz. Hunke and Dufowitz in 1997 at Los Alamos by adding elastic waves for efficiency and parallelism while retaining the same yield curve. And that approach was adopted by Warren for the DOE parallel climate model, which I will talk about shortly. It continues in the Los Alamos sea ice model in various forms. So the three-layer thermodynamic model was vastly simplified, but it still reproduced the average ice thickness over the year and the cycle of ice thickness through the year. And all it took was 3 layers, one snow layer and 2 ice layers, and a brine pocket which would absorb penetrating solar radiation in order to change the annual cycle to be roughly that is observed. And it wasn't until 1959 or 1997 that dynamics was actually able to be simplified. The viscous plastic Hibbeler method was simulated by Yusha Zhang and NGS, and using the Hunke and Dufowitz elastic viscous plastic rheology, the two methods were shown to give almost equal comparisons of sea ice concentration, the percentage of coverage. The vector correspondence is not quite as good, but the most important thing here is the ice coverage. And that is almost identical in both cases. Now there were some ocean ice speedups as well. Ocean speedups as well. When I took the Bryan and Cox model to UCLA, I completely rewrote it so that it could vectorize, and then I gave it back to them. And they used it for a number of years, because that was what they wanted for their Texas Instruments machine, which was a vector machine. At that time, the Cray machines did not exist, but this vectorized code worked also very well on Cray, the initial machine, and then on multiprocessor machines such as the XMP, YFP, and C90, with 4, 6, and 18 processors, respectively. And the key was a massive solid-state disk, which allowed you to do very large global 1/2 degree and 1/4 degree KKL's global run. And the thing about this is that if you consider 16 processors of a C90 running at 6 times faster than a scalar because of the vectorization, you get almost 100-fold increase in throughput if you're willing to take over the whole machine. And that was done at NCAR most nights and most weekends. So we got a lot done. We got these 1/2 degree and 1/4 degree models done. Then Smith, Dufowitz, and Malone in 1992 were attracted by this particular approach, and they had a massively parallel machine available, a connection machine 5 with 1,000 processors. They used about 512 processors in order to use a remapped version of the parallel ocean climate model on this machine, and the result was that they basically followed this dark line of progression down through the various parameterizations and variations of the original Bryan and Cox model. By contrast, over at GFDL, I believe MOM stayed with conventional technology longer So here's an early simulation that was done on the massively parallel machine, and now at 1/6 degree, and compared in terms of variation of sea surface height with Topek's early analysis of the same parameter. Topek's was so early that it did not have the degree of detail that the 6-degree model did. But longer integration, they came to agree much more, except in the North Atlantic, where the tendency of the model was to separate too far north and to extend too far across the Atlantic and not retroflect into the Labrador Sea. So now I want to talk about Warren's climate model. So in the early 1980s, their first climate model was a finite difference model, atmosphere and ocean, as I recall. And they were able in 1992 to go to a much more efficient spectral model, and they had it also parallelized by the version used for Bob Sherwood. They had a parallel vector 1-degree ocean model, 3-layer sea ice thermodynamics, and sea ice ocean, which was not dynamically simplified yet, was allowed to be that of a cavitating fluid. The most important thing is that these early climate change results were included in the IPCC second assessment report. And as most of you know, that is the real clearinghouse for information and scrutinization of information about climate change. And that was the early contribution that Warren's group made toward this, and not the last. Yeah, I wanted to point out that further advances on parallel vector computer architectures were blocked by an unfair ruling against the NEC in Japan. So the U.S. could not further continue its work on such parallel vector machines. Essentially, NEC introduced a machine at NCAR, and it was disallowed by politicking that I would regard as unfair. You remember that well. So, the next thing that was necessary was a complete response to this major architectural disruption. Here they were going strong. They expected a Cray to come out with 64 processors, but it worked poorly, and it was disallowed. And it was the only thing in town, but it was very expensive. So the response to this was to go to parallel climate model. I think this is probably one of the great achievements of Warren's leadership. He put together 3 institutions to collaborate and conduct extensive climate change simulations with even higher resolution atmosphere, ocean, and sea ice. The PCM model and its output were widely distributed and analyzed, and they contributed to both 3rd and 4th IPCC assessments for maximum global capacity. Can you all hear me back there? Okay, thanks. Tim Barnett, observational oceanographer at Scripps, did an unsolicited evaluation of the PCM. And this goes to Glenn's earlier question to me some months ago about how did improving the ocean really enter into anthropogenic climate change. And here it is. I've got 3 quotes from that paper by Tim Barnett. Large-scale increases in the heat content of the world oceans have been observed to occur over the last 45 years. The horizontal and temporal character of these changes have been closely represented by the state-of-the-art parallel climate model forced by observed and estimated anthropogenic. Observed anthropogenic gases. Application of optimal detection methodology shows that the model-produced signals are indistinguishable from the observations at the 0.5 confidence level. And finally, this suggests that the observed ocean heat content changes are consistent with those expected from anthropogenic forcing, which broadens the basis for claims that an anthropogenic signal has been detected in the global climate system. An unsolicited evaluation of PCM that is really glowing. Now, the NCAR director in 2000 dictated that the broader climate system modeling effort that was scaling up at NCAR be combined with Warren's effort. And this was to officially combine the expertise of all the individuals involved. The atmosphere was an updated CSM component, the ocean was an updated POP, and the ice was an updated sea ice. So 2 out of the 3 components were coming out of Warren's group. Warren and Jerry Meal became co-chairs of a new CCSM2 climate change working group, and they were also funded by DOE to do climate change simulations. So for IPCC AR5, CCSM3, as it was called, did integrations totaling 10,800 years with an even higher atmosphere and higher resolution atmosphere and ocean. Archiving and distribution of output was done mainly by DOE's Livermore Laboratory. Now, I just wanted to show one comparison of the 2 efforts back then. This is by Jerry Meal et al., including Warren as a co-author. And this is back in the days when you had those scenarios. For example, you could have flat CO2, you could have CO2 doubling, you could have even higher amounts of CO2 increase and level off at 2100. And then you could have the red curve, which is what we generally call business as usual, and which is something that is probably pretty well followed these days and may continue to be followed. The 2 models, PCM versus CCM03, CCSM03, differ in the respect of the amount of response they have to these different scenarios. But basically, anything above doubling of CO2 is going to get you above 1 degree C, and probably, since we're way up here already in terms of the scenarios, we're going to exceed the so-called acceptable 2 degree centigrade point before long. Now, sea ice also is allowed to increase in the simulation, which does not include the runoff from glaciers. And the sea ice just continues to grow even after all the other things have leveled off, just due to the warming of the upper ocean. This is not sea ice, this is global sea level rise. Now, if you include the glaciers, as I think we'll hear about further, then this scale could probably be increased by a factor of 10. And that would include the melting of the Greenland ice sheet from above and the melting of the West Antarctic ice sheet from below. So the next is just a summary of further developments. The NEC Japanese Earth Simulator was, I believe, one of the first machines on which it was possible to do 1/10 degree global ocean modeling. And that 1/10 degree ocean model was coupled to an improved atmospheric model having 50 degrees grid in CCSM4 for decadal studies in support of IPCC AR5. And finally, Warren and his colleagues migrated a new configuration of climate Earth system model onto a petaflop DOE machine at 1/4 degree in the atmosphere and with eddies parameterized at 1 degree in the ocean. And century-long simulations with differing CO2 increases are being analyzed today, as far as I understand. Furthermore, down the line, not yet in progress, DOE exascale models will allow long integrations with land ice added some cloud resolution, and full ocean resolution. And Ruby Lynn will talk about that next. So here's a quick summary of the developments that have occurred over the course of Warren's career under his leadership. Sea ice progression has gone from efficient thermodynamics to fully explicit parallel EVP dynamics. Ocean progression has gone from global ocean models with no eddies to partly resolved eddies, and finally well resolved at 0.1 degree. That's a huge computational requirement. And historical coupled model progressions. Atmosphere over ocean, with green versus blue, have gone from 5 by 5 initially, all the way down to where you see the PCM at 2.8 over 0.67, CCM3, CCM4, and CESM. CESM has backed off on ocean resolution just in order to be able to have higher atmospheric resolution. I think the bottom line here is that impressive increases in resolution are mainly due to the pioneering efforts of Warren sponsors and collaborators to develop new algorithms and to adapt to changing computer architectures, thereby facilitating vast numbers of Warren's high-quality simulations for IPCC assessments. Thank you. Sure.